I'd like to review the physical properties of minerals. And this should be review for every one of you because you would have covered the physical properties of minerals and used those physical properties to identify minerals in your Geology 101, 104, or 110 lab. The first group of physical properties that we can use to identify minerals are all related because they are controlled by the atomic structure in the minerals and the kind of bonding. So whether you have a metallic, covalent, or more ionic bond. And those things would be the hardness, the tenacity, striation, where they have striations in the minerals, whether you see twinning, habit, the density of the mineral, what kind of cleavage it has, whether or not you see double refraction in something like optical calcite, whether there's magnetic attraction to the mineral, and what kind of fracture it has. And the images that I have here show striations on crystal faces of pyrite. These striations are actually a result of twinning and feldspar, and then the double refraction in calcite. Now, when we talked about habit, assessing habit optically, I suggested that just a few terms for habit were adequate to describe what you can see in thin sections because you only have 2 dimensions, but in hand specimens, you oftentimes see a lot more of the mineral. You're seeing 3 dimensions of the crystal, and there are many more terms that you can use to describe habit. So for instance, a cubic or equant habit, if it is stubby but not cubic, you might refer to habit as blocky. Acicular, if you have a needle-like habit. Prismatic or columnar. In micas, a platy or micaceous cleavage. In kyanite, this isn't kyanite, but a bladed habit where you could think of a stick of gum or a knife blade. It's long and flat. A tabular habit, I have another example of tabular over here on the right, where it looks like a little book. It's flat and it's thick. An octahedral habit, you could also use equant to describe this. Rhombohedral, most often you'll see rhombohedral cleavage in calcite. A granular, or you could call this a massive cleavage. Granular cleavage meaning you can't really identify a particular habit, but it looks like small grains of indistinct habit. A fibrous habit, dendritic, that looks like branches of a tree. A radiating habit, botryoidal, so globules or it looks like clusters of grapes. Garnet, we often see the dodecahedrons, again, cubes of pyrite. Striated is one way to describe habit. Prismatic, if you see euhedral faces of a nice crystal form, or some of those faces, you might call it prismatic. And then here's another example of radiating down here. You see there are a lot more terms, and this isn't all of the terms. You'll run across others. But these are the most common, and even then we won't probably use all of these, at least very often. Now, hardness you're also familiar with because you've used hardness tests to identify, to help you identify minerals. And this is also related to the atomic structure. And minerals that have strong covalent bonds are some of the hardest minerals, and softer minerals have metallic or van der Waals bonds. And you're going to test hardness using either other minerals of known hardness, one of these on the Mohs hardness scale, or using your fingernail for very soft minerals, a penny, a glass slide, or a knife blade, or a streak plate, or a steel file. Now, realize that not all knife blades or steel files are going to have exactly the same hardness because they might be made of different alloys. So these are approximations. Most commonly, you'll see single planes of cleavage in the micas. Here's muscovite, for example, that breaks along the basal plane into sheets. Feldspar has two cleavage planes at about 90 degrees. You'll see three planes in calcite or halite, where you have a rhombohedral or a cubic cleavage. Four planes in fluorite, and here you're seeing octahedra of fluorite, and six planes in sphalerite. And of course, you're not going to see all of these planes of cleavage most of the time unless you have a very nice, well-crystallized mineral. But sometimes you'll see, even if the external faces don't reflect the cleavage, that fractures or those cleavage planes will be visible inside the crystal that you're looking at. And you'll get used to this when we look at these minerals in class. The fracture, now not all minerals have cleavage. Some, like quartz, don't have cleavage, but they fracture, and they have an irregular fracture, or we might see a conchoidal fracture that looks like when glass breaks. That's when you're most familiar with. Quartz has that nice conchoidal fracture. You might see a fibrous fracture where small fibers can be broken off from the mineral. Or oftentimes you're not going to be able to assess the fracture. You'll just see irregular surfaces that clearly aren't cleavage planes. And of course, I don't want you trying to determine cleavage and fracture by actually hammering on our mineral specimens. So we will look at fracture and cleavage and assess it as best we can with the mineral specimens. You'll see twinning. Now, the kind of twinning on the right, these penetration twins, are not terribly common, but occasionally you'll see it, and occasionally you'll see it in thin section. So you should be aware that of what it looks like. More often in hand specimen, you'll see striations on plagioclase or other minerals on nice flat cleavage surfaces, and that tells you that there's twinning and distinguishes minerals like plagioclase from similar looking K-feldspars. Some minerals have the property that they are magnetic and can attract a magnet. Most often it's magnetite. Pyrrhotite is also one, and that's because of the iron bonds. And realize too that sometimes your magnet will, a mineral specimen will feel slightly magnetic when it's not magnetite, because there might be inclusions or other minerals in the specimen that are actually causing the specimen to be magnetic. So be careful what you're testing. The tenacity is the resistance to breaking, and most of the minerals that we're going to look at are brittle. They break and would powder easily, for example, quartz and feldspar. Some can be malleable, like this copper, but again, we're not going to destroy our samples and actually try a lot of this. Some other terms: sectile, ductile, flexible, elastic. If this is something that you can see in the specimen that you have, you can assess it. If, for example, with biotite and muscovite, you can see in the sheets that they're elastic, that you can bend them and they'll return to the original position. But as far as chlorite being flexible, I don't have any specimens that are large enough for you to test that. But so you'll have limited ability to test tenacity, but it can be helpful. Now, another group of physical properties that are controlled by the kinds of atoms that are in the mineral, and those include the specific gravity, the color, whether a mineral fluoresces, a taste or smell, or whether it's soluble in acid. Basically, does it pass the fizz test? Now, color is notoriously misleading for identification because, number one, many minerals have different colors. And this is caused because the color itself is caused from the absorption or lack of absorption of different wavelengths of light. And if it is absorbed, the light is leaving the crystal and it's not going to be white anymore. More importantly, what controls color are the trace elements that are in the minerals. And oftentimes these are the transition metals. But just some examples, chromium produces an orange-red color in some minerals, like this crocoite, but chromium produces a green color in fuchsite, which is a chrome-bearing white mica. Not white anymore because of the chrome. Iron produces the red color in limonite. Manganese produces a pink color in rhodochrosite. Copper produces a blue color of azurite. Copper also causes the green color in malachite. So even small amounts of these elements can change the color of what you're looking at. And so you have to be very careful how you treat color. You can't use just color to identify most minerals. Specific gravity. Okay, there's a lot of words to say that basically specific gravity is the weight of that mineral compared to the weight of the same volume of water. And you're not going to measure this in class, but we will use we'll estimate the specific gravity based on the relative heft of the mineral. So whether a small piece of barite feels very dense compared to the same size specimen of feldspar. You could compare the two side by side and feel that barite has a higher specific gravity than feldspar. So we are going to just use this in a relative way and call a mineral either high or low specific gravity. And see too that the specific gravity is controlled by the composition of the mineral. For example, with increasing atomic weight for the cations if you look at aragonite, which is a calcium carbonate, has a much lower specific gravity than related minerals with related structures that have higher atomic number elements. So the strontium, barium, and lead are higher atomic weights, and you see that the corresponding specific gravity increases. And same down below with anhydrite, which is a calcium sulfate. You substitute strontium, barium, and lead into that same position in the crystal to get these different minerals, and you see the increase in specific gravity goes along with that. Calcite is most commonly identified, if you can't see the cleavage surfaces, by putting a drop of hydrochloric acid on the specimen. And it's often a test that people forget to do when they're stumped. And sometimes that's because calcite has a different color. Taste. You're not going to taste every single mineral in class, but it can be helpful, especially when it comes to halite and sylvite. Halite is table salt, so it tastes salty. Sylvite is also a salt, but it's more bitter than halite and can be used to distinguish the two. And I recommend that you try it. If you can wipe off a little area of your mineral specimen and give it a shot. This group of physical properties is associated with light, and those are the luster of a mineral, whether it's iridescent, whether a mineral is transparent, what kind of streak it has, and whether it tarnishes. So you can see, as far as transparency, this mineral specimen, you can not only see light passing through it, but you can see what is on the other side. So you can actually view through the crystal to the other side. And that property is helpful. Luster is a tricky property to describe, because there are lots of different ways to categorize luster, and depending on your mineral specimen, you'll see different things. Like if you have a cleavage face on your mineral specimen, you would assess the luster differently than if you're looking at a fractured surface. But in general, we break luster down into metallic lusters and non-metallic lusters. And metals, you know what metal looks like. A metallic luster is easy to identify. And submetallic, if it's a dulled metal, for example, by weathering or corrosion, or minerals like graphite can also have a submetallic luster. Look at the tip of your pencil to see some graphite. Non-metallic lusters are more complicated. The ones that we'll probably use most often are dull or earthy, whether they don't have any shiny surfaces. It is looking like a clay or soil. We'll also use adamantine and glassy or vitreous often. Adamantine is when it has a gem-like quality, a sparkle or a very shiny surface, or glassy and vitreous. It's looks like glass. Also shiny, but not as shiny and not as brilliant as the adamantine. Amber looks resinous, and that's a good image of amber, so you can see what resinous looks like, and you can compare your specimens to these images. Some minerals will have a greasy or an oily look, or a silky look. This is a good example here with gypsum. Some minerals will be iridescent. Some will be pearly. But, like I said, I don't use all of these all the time. Stick to simple. Streak. So this is the color of a finely powdered form of the mineral that you're looking at. And it's very helpful, particularly with a mineral like hematite, when it comes in different varieties. And the hematite on the right that looks rusty red maybe looks more familiar to you than the specular hematite on the left. But the streak will give up the secret. We use a ceramic streak plate for testing this, and of course the streak plate has a given hardness, and you'll only be able to powder your mineral if the hardness of the streak plate is higher than the hardness of the mineral that you're trying to test. Now, what you learned was that certain physical properties of minerals are controlled by the atomic structure and bonding. Those are habit, hardness, cleavage, fracture, twinning, tenacity, and magnetism. Other properties are controlled by the kind of atoms that are in the crystal. Those are color, specific gravity, acid solubility, taste. And properties that are associated with light are luster, transparency, iridescence, and streak. So what I'd like you to do is to go get the physical properties image file that is on iLearn and complete the quiz on physical properties of minerals. Now, because you can't test the mineral specimens online, we're going to focus on just a subset of these physical properties. But I'd like you to practice those with the quiz and be ready to test the other properties in class afterward.